Last night you were supposed to watch the naming video for homework, and we're going to spend most of 2 periods today practicing this stuff. But I'm going to give you an extra walkthrough tutorial video now on naming, so you have a few more examples to look at. First off, just remember the rules. Before you can do anything, just look at your molecule and see what's actually in it. How many different types of elements are there? Are there only 2 types of elements? Are there more than 2 types of elements? If there's just 2 types of elements, you could either have a metal and a nonmetal, or 2 nonmetals together. If you see more than 2 types of elements, usually only 3 or 4, you'll have some kind of polyatomic, and you go to table E in your reference table, that's on the back of the front page, and look for what in the molecule counts as a polyatomic ion. It counts as one of those larger pieces with a charge overall, something like OH minus, where there's multiple atoms with an overall charge. First, let's go through the rules. Like I said, first scenario is maybe you have a metal and a nonmetal. If you see 2 different elements and only 2 different elements, and again, we're not caring about how many of the element there are, so it doesn't make a difference whether you're talking about NaCl, where there's 1 metal and 1 nonmetal, or if you have something like MgCl2, where there's 1 metal and 2 of the same nonmetal. It doesn't matter, just there's 2 different elements, 1 and 2, and 1 and 2. If it's a metal and a nonmetal, you always keep the name of the metal the same. You don't change anything. So NaCl, you'd call it sodium chloride, and MgCl2 would be magnesium chloride. You keep the metal name the same. The nonmetal, the second part of the molecule, like the chlorine in these 2 examples, you just change the ending of the nonmetal's name to IDA. So instead of chlorine, you could call this chloride. If you had fluorine, if it was NaF, you'd say fluoride. If it was NaI with iodine, you'd say iodide, and things like that. The second nonmetal in the name, the thing that's on the right, you change the ending to IDA. Also, if the metal has multiple positive ions, that's when you use the Roman numerals to Stochastic. I'll show you that in a second on another slide. And that's probably going to be what most of you have questions about, because that's where it gets a little tricky. You just have to remember what to do. But after you name these things, after you follow the rules on this slide, just go back and check. If there was a metal in the molecule, does that metal have multiple possible charges? So just go to your periodic table after you use these rules to name it and see, does the metal have multiple charges? So like I would look at Na on my periodic table and see that it can only form a +1 charge. That's all it's ever going to be. You don't need any extra detail. That's the only option. If you looked at copper, copper can be either a +1 or a +2 charge. You have to give a little more detail there. You can't just say copper. You have to say which version of copper was it. Gold. Gold has a +1 or a +3. You have to say which one that is. Aluminum can only ever be a +3, so you would just have to say aluminum. You don't have to give the extra detail. But those Roman numerals for the Stoch system are only in that event. If the metal that you have in your molecule has multiple forms, then you just have to add that extra detail. I'm going to go to the number 2 now. If you see more than 2 elements in your molecule, something's going to be polyatomic ion. Go and look, where is the polyatomic ion? So just go and check your table E and compare them and say, what on this table do I see in this molecule? So just start at the left. Are these 2 elements next to each other a polyatomic ion? Are these elements next to each other a polyatomic ion? What is there? Use your table and just compare it and see what actually is it that's in the molecule. And just like with the metals, polyatomic ions have their own names. That's what table E shows you. Keep the name of the polyatomic ion like it is and don't change it at all. So keep the metal names the same in any molecule, keep polyatomic ion names the same in any molecule, and then the nonmetal on the right side of the molecule, the thing written second, because remember you do positive things first, negative things second, nonmetal names then get their endings changed to IDA. The third and final option is if you look at your molecule and there's 2 different types of elements and they're both nonmetals. So you look at where they are on the periodic table and both the elements in your molecule are on the upper right of the table, on the right and above the staircase. Those are 2 different nonmetals, and that's where you use the prefixes. So I gave you that little prefix chart in your notes on the video, and you can hear me shuffling my pages. I'm going to look at my reference table. On page 7 of your reference table, table P does list some prefixes, but this is where I said in the video, they're not totally the same. Numbers 5 through 10, pent, hex, hept, oct, non, dec, those are the same. But these are the organic prefixes, so 1 through 4 are a little bit different. So you just have to remember those first 4 if you have to. If you can't memorize them, just there's no really where to look for them. You just got to memorize those things and know it's mono, di, tri, and what's it, tetra. Different from the organic ones that are on the chart. Everything else 5 to 10 after that is the same. And then just use those to say how many of something you have. So like, I'm making this one up, P2O5, phosphorus, you just write phosphorus. There are 2 of phosphorus, so I would see that the prefix for that is di, so I'd write diphosphorus, and then oxygen, remember it's written second, so I change it to oxide, don't write oxygen, and there's 5 of it, so I'd write penta, and because it's, instead of writing pentaoxide, you have those 2 vowels next to each other, you can just combine them and just make it pentoxide. You don't have to write both vowels, the A and the O. It doesn't be pentaoxide, just pentoxide. If you write pentaoxide, it's fine, but you usually just see it with the two vowels combined into one. And the other thing to remember about the two nonmetals is that if the first element only has one of it, you don't write mono. So normally you'd write mono, so like this one would be carbon monoxide, monoxide, but you don't write monocarbon monoxide. Just like CO2 is carbon dioxide for two oxygens, not a monocarbon dioxide. So prefixes for your nonmetals if it's only nonmetals and only two different nonmetals, and don't use mono for the first element. Okay, so I said stock system is probably what you're going to have the most questions on, and this is where it gets a little bit tricky just as a last step. After you name something, just you have to go back and double check, are there multiple forms of the metal? So if I told you we want to combine ions of manganese with ions of chlorine, and we want to see what kind of ratio they'll form, what do the molecule look like when we combine these things, we can do the crisscross method, and by now you should be able to do that. But we've got some options here because as you can see, manganese has 4 different ions it can form. Now chlorine has to be a negative ion to go along with the positive metal, and chlorine only has one form of the negative ion, so you don't really have options there. But manganese, you could combine a +2 manganese with chlorine, you combine the +3 version of manganese to chlorine, you combine the +4, the +7 versions of manganese to chlorine, and they're all going to look a little bit different. So for example, if we take manganese, and let's just do the first one on the list there, take the manganese, the +2 version of it, and combine that with the chlorine -1 ion, you do your crisscross, and the 1 from the charge of the chlorine goes down to manganese. The +2 from the charge of the manganese goes down and tells you need 2 chlorines. This right here is a neutral compound. If we did, let's say, the +7 version of manganese over here, manganese +7, and combine that with the chlorine -1 ion. Again, if we do our crisscross, the 1 from the chlorine's charge will go down next to the manganese, and the +7 from the manganese's charge will go down next to the chlorine, and that's another molecule. So we could have either MnCl2 if we use that version of manganese, or we can have MnCl7 if we use that version of manganese. Now, by the rules of looking at this and seeing what our pieces are, each one of these molecules has 2 elements, 1 metal, 1 non-metal. So by the rules we saw before, I'm going to keep the metal name the same, and this would be manganese for each one. And then it said change the ending of the nonmetal to IDA. So I could call this manganese chloride, and I could call this one over here also manganese chloride. So the trouble is these two things look very different from each other. If you were a doctor or scientist and you're trying to give this as a drug or something, you got to pull this bottle off the shelf. How are you going to know which molecule is which? If I say go get manganese chloride, you go to your stock room, which one do you pick? You've got 4 different options. I only drew 2 of them, but there are 4 different options here. That's not counting any ones that may not even be listed on your reference table. This could be the difference between life and death if you're trying to give a drug to somebody, if you're trying to make a medicine for someone. So we need to know which version of it we have. To do that, we now just go back and check our table, and we would see again that manganese has these different 4 versions here. And we just want to add a little bit of detail to say, well, which version was it that we used? So I'm just going to cross this off for a second here and change. Actually, I don't have to do that. I'm going to erase that line. Ha! My pen has a nice little eraser. I don't ever really use that. I'm going to add a little bit more detail here. Let me actually switch to a blue ink to show this detail change. And because the original ion of manganese was the +2 version, I can call this manganese, and then in parentheses Roman numeral 2 chloride. It's not how many manganese we have. You see right here, there's still only 1 manganese. But it's the original charge on the manganese ion that formed this molecule is +2, so it's manganese 2 chloride. Same thing over here. The original ion of manganese we used was the +7 version. That's why there's 7 chlorines in the molecule. So I'm going to write manganese, and now in parentheses, Roman numeral 7. That's V for 5, 1 for 6, 1 for 7. VII. Manganese 7 chloride. Again, it's the charge of the manganese in the molecule, not the number of manganeses in it. There's only 1 manganese, but it's the charge of the original ion is written by the Roman numeral in parentheses. And really this thing now helps us go backwards. If someone else saw what you wrote here, they could go backwards and figure out exactly what these molecules look like. Because if they see you write manganese with a Roman numeral 2, they could then write on their papers manganese +2. And they would see the word chloride and know that that means it's chlorine as an ion, so they would go look up and know that chlorine looks like that. And now they can do the crisscross themselves and get MnCl2, just as we did up here. They reverse engineered what the molecule looks like. Same thing over on the right side. They see manganese with a 7 Roman numeral, they would write Mn with a +7, when they see chloride rather, they write Cl minus. They do the crisscross, and now it's MnCl7. The names tell us exactly how to write the molecule, and the molecules let us figure out the names. As long as we have a periodic table with the charges, we can do this, and you always will because that's given to you, as I've been saying since day one. So hopefully this makes a little more sense, and now you've got a bunch of practice we're going to do. So in case you don't figure it out when we do this in class, I enjoy this stuff just because it's very formulaic. Once you get the hang of it, once you practice it, you just do the same thing every single time, and you can always find your names. There's going to be a couple of examples, maybe you'll see that are a little bit weird, and I'll tell you, don't do this, or you'll ask me, why does this not make sense? And I'll say, oh yeah, right, that one on the form is strange, ignore that one. But 99.99% of these things, you do the same thing every time. You just start with your formula, see what elements are there, how many elements are there, what am I looking at? Is it a metal and non-metal, two non-metals, or same with the polyatomic ion? Follow the steps the exact same way, and then just go for it. And just once you get the hang of it, it's going to be a lot easier. So I'm just going to do all these. I mean, what's this? 12 examples here, and there's some more on the next slide where we're going to go backwards from the names and make the formulas, and we're just going to run through them. So keep watching if you want to. You can jump around, and hopefully this helps if you need the help. So first one on the top left, Na2S. I'm going to look at my formula. It says I have two different elements, the Na and the S. Now I know there's no polyatomic ion, so I'm dealing either with a metal and non-metal or a non-metal non-metal. I go to my periodic table if I have to, and I see that Na is a metal and sulfur S is a non-metal. Now I know I keep metal names the same, so I'm going to write Na as sodium. And just because there's not a ton of room on this page, I'm going to write the names underneath each other. Na is sodium, and then the S is sulfur. I know by my rules that the non-metal, I change the ending of the name. So instead of sulfur, I'm going to change the ending of this to sulfide. I really like the eraser on this pen. I don't use it nearly enough. Fun. I wish I had it on the whiteboard. So sulfide, I'm not very happy with that U either, so I'm going to erase that also. Look at that. Sulfide, sodium sulfide, that's it. All the information we need. If somebody else wanted to figure out what this molecule is looking like based on that name, they'd see sodium, they could write Na with a plus. At the end, I could go and double check, and sodium only has one option for a charge, so you don't have to use a Roman numeral at all. That's what sodium is going to look like, Na plus. And sulfide, the "-ide ending tells anybody looking at it that's a non-metal that you change the ending of. They're going to go see what the charge of the sulfur ion is, and it would be S with a -2 charge. And when they do the crisscross, they'd end up exactly as you had to begin with, Na2S. Everybody gets the exact same answer because you're all using the same exact system. Anyone anywhere is doing this exact same thing. Next example, AlCl3. Again, how many elements? I see two elements. I see Al and I see Cl. Al, based on my periodic table, I know is a metal. Cl is going to be a non-metal. So I know by my rules, I'm just going to name the metal. That's aluminum. And then I'm going to call it chloride. Change the chlorine to chloride. Now as my last step, I just go check my periodic table to see does aluminum have multiple options that we have to account for. Aluminum, the periodic table tells me, can only ever form a +3 ion. That's why there's a little 3 down here next to chlorine, because the +3 charge of aluminum got crisscrossed down to tell us we need 3 chloride ions. But that's the only option, so we don't have to get any more detail. Anyone trying to figure out what this molecule looks like from this name would only know there's one option for aluminum, one option for chlorine. It's only ever going to look like AlCl3. There's no other versions of it. So we're done there. Next one now. Two elements. So again, no polyatomic ions to look, nothing on table A. What are my elements though? B and Se. I look at my periodic table and I see that both boron and selenium are nonmetals. It's the first example now we've done where it's all nonmetals. Nonmetals, we use prefixes. So I'm going to write just first the names, boron, and then I'll add a prefix to that in a second. I'm happy with this R and this O, so let me rewrite this. Boron. And selenium is the other one. And I cannot write. Selenium. Now, it's the second nonmetal in the second part of the name, so instead of selenium, I'm going to change the ending again to IDE, and it actually becomes selenide. It seems kind of weird. Some of these elements is going to look strange, but once you get used to it, you'll figure out it doesn't actually look as weird. Some like chlorine makes sense, just chlorine, chloride. Selenium to selenide, tellurium to telluride. It's going to look strange and sound strange, but just go with it. All right, we've got our elements listed. Now we have to just write the prefixes. So 4 for boron and 5 for selenium. It's not asking what's a charge. It's just saying how many of them actually are in this molecule. 4 for boron. So it's not on the reference table. You just got to remember this one because it's one of the first couple elements. On that chart I gave you, 4, the prefix is tetra. So tetraboron. 5 for selenium, it's penta. So we write penta like pentagon, pentaselenide. So tetraboron pentaselenide. Again, anyone seeing this and wanting to figure out what this thing looks like is going to read, oh, tetraboron. I see boron, that's B. Tetra means 4, so I'm going to write the 4 here. And then they're going to see the selenides, they know it's going to be SE, and they see the penta, so they know it's going to be 5 there. That's as easy as it tells you the directions. It's basically telling you the recipe just in its name. It's like if you go to some restaurant, you see like you're going to order beef with broccoli. That's telling you exactly what's in it. It doesn't have some fancy name. It tells you exactly this is what you're getting. Bacon cheeseburger means you're getting a burger with bacon and with cheese. There's nothing hidden there. There's some stuff you may not want to know is in it, but it's telling you the main ingredients right off the bat. Tetraboron pentaselenide does the exact same thing. It tells you what you're getting in the molecule. I'm going to erase this so I have some more room to play with over here, and then finish the last example on the line here. And again, I see that we're up to 16 minutes of this video already. If you don't need the help, don't bother watching this video. Feel free to flip around, skip around or turn this off at any time. But if you do need some help with this, I'm just doing this for the heck of it because I've still got time for the bell rings. CaCO3. First step, count my elements. I see calcium, carbon, and oxygen. I see multiple capital letters, 3 different elements. So now for the first time I see that something in there has to be polyatomic ion. So I'm now going to turn to table A on my reference table. You can hear me shuffling the papers. You should be doing the same. And I'm going to just look through it. I'm going to just read left to right. Is CaC a polyatomic ion? I'm going to check my reference table and I don't see that on here at all. So that's not the polyatomic ion. Something else has to be. Well, maybe C and the O's are polyatomic ion. And right on the left-hand side, I see that CO3, this piece right here, is listed as the carbonate ion. It's actually, can't fit on the page, but that's actually the CO3 with a -2 charge ion. So that's what we're talking about. We're talking about carbonate now. So that's going to be this one piece. We know from our rules before, we now have a metal and a carbonate, and the rules tell us that we keep metal names the same. So I'm going to write calcium. And the ion names stay the same also, so I'm going to write carbonate. As a last step, I go and just check, does calcium have any multiple forms of the ion that I have to account for? And on the periodic table, it tells us that the only form of calcium is +2. So I don't draw any more detail. With that +2 charge, though, where'd it go? Because if we had calcium +2 and the CO3 is a -2 ion, where'd the 2's go? Well, if I do my crisscross, I'm going to bring the 2 down here, I'm going to bring this 2 down over there. It would initially look like Ca2, CO3, and I need it right in parentheses with the 2. But because these numbers are exactly the same here and here, we can reduce it. You get rid of that 2, you get rid of that 2, and then you also don't need the parentheses, and it just becomes CaCO3, and that's exactly what it looks like here. So you reduce the numbers. It's a lot of stuff to do, but you can always kind of work backward and forth and double check your work. If you cold calcium carbonate, calcium, what's that look like? Ca +2. Carbonate, what's that look like? CO3 -2. Do your crisscross, and you'll eventually end up with CaCO3, exactly as it was in the first step. So it's a little bit of extra stuff to do, but really only if you don't feel comfortable with and you want to recheck your stuff. Otherwise, it's fairly straightforward, that one. KCN, I've got 3 different elements, so I know there's going to be some kind of polyatomic ion, and on my reference table, it shows me that Cn is the ion. So now we've got a metal and a polyatomic ion. Metal names, remember, stay the same, so potassium is K. And then I see on my table that Cn is the cyanide ion. I check the periodic table. Does K have multiple charges? It does not, so I don't need any Roman numerals. And the whole name is just potassium cyanide. P3F8. 2 elements, so it's either metal, nonmetal, or nonmetal, nonmetal. I look at my periodic table and see that they're both nonmetals, so I'm just going to use some prefixes. So I'm just going to write phosphorus. And I'm going to write fluorine. Remember, the second nonmetal gets the ending of its name changed. So I'm going to erase the ending and make it fluoride. And now we just have to account for how many of each one there are. 3 phosphoruses, so triphosphorus, and 8 fluorines. The prefix for 8, like an octagon, is octa, or octopus, octafluoride. Triphosphorus octafluoride. No crisscrossing, it just says there are 3 phosphorus and 8 fluorines, triphosphorus octafluoride. So I'm going to jump around to, which one I want to do? The bell's going to ring in a second. Let's do the bottom one here, H3O SCN. There's all kinds of elements in this. I count 1, 2, 3, 4, 5 different elements. So there's definitely a polyatomic ion in here somewhere. I'm going to look at my table, E, and it says right at the top, H3O is an ion called hydronium. But this other piece here, we still have 3 elements. So what the heck's going on there? Well, I look a little bit down the table and over on the right-hand side, and it tells me SCN is also a polyatomic ion. So no rule says you can't have 2 of these things. So this means you have a positive polyatomic ion, the H3O, and you have a negative polyatomic ion, the SCN. So now we've just got to use the names for both these things. There's no nonmetals, no metals in this, just 2 polyatomic ions. H3O, we look, and that is called hydronium. And the SCN we see on the other side of the table is called thiocyanate. It's a great name. Hydronium thiocyanate. Anyone who wants to figure out what this thing looks like, they go and look at what hydronium looks like. They'd see H3O plus. They'd go look what thiocyanate looks like. They'd see SCN. There's the bell. SCN minus. They do a crisscross, and you get H3O SCN. Because there's only one of each, they cancel out. You don't have any parentheses needed. And right there, hydronium thiocyanate is your molecule. That was the bell, 7th period starting. I'm about to have a bunch of freshmen, sophomores busting on my door. So I'm going to finish this comments. And in the meantime, I will see you for 8th period and most of a double to talk about snow, talk about blue powders, and talk about this. So I'll see you in 40 minutes, 44 minutes. Okay, the day is over. You guys left. For the 5 of you who watched in the first place and the 3 of you who watched for more than a couple minutes, thanks for paying attention and sticking with us. Let's do some names back to formulas. So same kind of thing. Just see from the name, what's it look like, what's it trying to tell you. You go in reverse now, trying to figure out a formula from the name instead of name from formula, but the same kind of rules are going to apply. So right here I see zinc oxide, and that's telling me I know what zinc looks like. I can go look that up, and I'm trying to figure out what oxide looks like. So grab your periodic tables. We may have to go to table E at some point, but like I said in class today, the names tell you exactly what's going to look like. It gives you all the information you need. We'll see that later on in the year too, and we do the same kind of thing in other chapters. But the name tells you everything you need to know. So zinc tells me exactly what I'm looking at. That's a metal, so I'm going to go to my periodic table, and I see that zinc, which is Zn, has a charge of +2 only. It's the only kind of charge zinc ions will form. And then I see oxide. If you want to check your periodic table with the polyatomic ion chart, rather, you're going to see that oxide is not on there. So oxide is not a polyatomic ion. Oxide is just where you change the non-metal name ending to IDE. So that means it's oxygen. We're going to look at oxygen, and it says that O forms a -2 charge to go along with the zinc with a +2 charge. So we're going to crisscross. We'll have Zn and O, and we just want to see what the numbers are next to them. So the 2 from zinc, we're going to crisscross down, put next to the oxygen, and the 2 from oxygen, we're going to crisscross down and put next to zinc. If you notice anything about these 2 numbers, we see that the 2 and 2, the subscripts in each element, can cancel out. So we can just get rid of those 2 numbers, and we're left with 1 each. And because it looks like I drew oxygen a little bit farther out because I knew I was leaving space for the numbers, let me just rewrite over here, and zinc oxide will be ZnO. You notice the name zinc oxide does not have a Roman numeral because zinc only forms 1 ion, so you don't need any extra information. You don't need any extra details. It's just zinc oxide. It's the only thing that's ever going to look like. Next one, carbon non-oxide. Again, look at it, say, what do I have here? Carbon's a nonmetal, and oxide means it's going to be oxygen. You see the prefix, so it's 2 nonmetals. That's exactly what we have here. Nonmetal and nonmetal, this is where we use the prefixes. So carbon and oxide means oxygen. Now we just want to figure out how many of each one. The first one, carbon, has no prefix. That means that it's 1 in the first thing, just like carbon dioxide You don't say mono if the first one only has one. So if carbon in the first thing only says carbon, that means there's only one carbon. We don't have to write a number. And then non-oxide, you have to either check your chart, but mostly you have to memorize things because not all on the reference table. Non is the prefix for 9, as it sounds like it is, and we write CO9. So carbon, no prefix, that means there's one, C, and then non-oxide means 9 oxygens, so CO9 is our formula for carbon non-oxide. Lead 2 sulfate. Again, it's telling you exactly what there is. Lead, Roman numeral 2. I'm going to look up lead, and it's Pb. And I'm looking at my lead on my periodic table. It tells me it can either be a +2 or +4 charge. How are we supposed to know which one it is? Well, just because it tells us right here. Roman numeral 2, that means it's the +2 charge. And then sulfate, that's not a nonmetal that I'm aware of, and I don't see an "ide" ending, so there's not that we change the ending of a nonmetal name to IDE. So that means that sulfate is probably a polyatomic ion. So I'm going to again turn to table E in my reference table, and if I look on there, I do in fact see something called sulfate, and that's SO4 -2 charge. So I'm going to write SO4 with a -2 charge. Now I can do my crisscross to see exactly what this would look like when it comes together, and I'm going to write Pb here and SO4 here. And again, we want to now figure out what, if anything, is going to go down next to these things. So I'm going to take the 2 from the charge of lead and drop that down and put that outside here. I'm going to put parentheses around the SO4, show that there's 2 of the entire SO4. And I'm going to take the 2, which is the charge of the SO4, and move it down to show that I have 2 of the lead atoms too. And then again, looking at this, we see 2 and 2, those numbers will cancel each other out. So we don't even need to write these numbers, and I can erase all this stuff. My entire molecule just looks like PbSO4. The Pb has a +2, the SO4 is a -2. They go together, 1-to-1 ratio, balance and cancel, and that's my lead 2 sulfate. Trinitrogen monosulfide. Again, we're looking at prefixes and prefixes. That's going to tell us we have a nonmetal over here and a nonmetal over here. So now we can go and just follow exactly what these things say. Trinitrogen. Tri is the prefix, nitrogen's our element. Mono is the prefix, sulfide is our element. So trinitrogen means there's nitrogen, and tri is the prefix for 3, so I'm going to write N3. And then sulfide, that's just changing the IDE ending on sulfur, so I'm going to write the S for sulfur. It's a terrible looking S. And mono is a prefix for 1, so there's only one S. I live exactly like this, N3S. Trinitrogen monosulfide. Use the prefixes, I change the IDE ending on the second nonmetal. Trinitrogen sulfide. Next one, sodium nitrate. Sodium right here. That's a metal I know, because I can see on the reference table. And sodium has only a +1 charge. I don't have to do anything there. Nitrite. It's not an IDE ending, so it's not that we just changed the nonmetal ending to IDE. So nitrite, I'm pretty sure is going to be a polyatomic ion. I mean, I know it is, but for you, you should be hopefully kind of sure, thinking it might be a polyatomic ion, at least getting that idea, sense of it, and go and check your periodic table, and your reference table. Table E for polyatomic ions does show nitrite is NO2 with a -1 charge. NO2 with a minus charge. So I'm going to write that right underneath here now. Sodium is Na+. Nitrite, not to be confused with nitrate. Careful, there's a couple that look alike. Nitrite, with the I, is NO2 with a -1 charge. I'm going to do my crisscross, and I get Na down here, and NO2 with some number. The plus charge from Na goes down there, and it would just be a 1, so I'm going to leave that exactly as it is. And the 1 charge from the minus of NO2 will go down there, and again, it would be some number over next to sodium, but that's, I'm going to leave that where it is too, because it's just going to be 1 for each one. So MaNO2 is our molecule, sodium nitrite. Next one, aluminum phosphate. Aluminum is a metal. I'm going to write Al, and I can see on my periodic table that aluminum has a +3 charge. Phosphide, I think I said phosphate a second ago. It's phosphide. IDE ending means we just changed the ending of a nonmetal. So phosphide was originally phosphorus, so it's just going to be a P. And again, I can see in my periodic table that the negative charge of phosphorus to go along with the positive charge of aluminum is a -3 charge. Periodic table tells me on the top right corner. So now I'm going to crisscross, I'm going to put the 3 from aluminum down there. I'm going to put the 3s from phosphorus over here. And I get Al with a 3, P also with a 3. And now again, just last step, can we reduce this at all? Well, I see 3 and 3. I can definitely take those numbers out. So I'm going to get rid of the 3 there. I can get rid of the 3 right there. And my compound is just ALP. The plus 3 from aluminum and the negative 3 from phosphorus cancel. 1-to-1 ratio. ALP is aluminum phosphide. Ammonium hydroxide. I think we did this in class today. This does not look like a metal name that I'm aware of. This does not look like a metal or non-metal name I'm aware of. So I can check my polyatomic ion chart. And table E does in fact tell me that ammonium looks like MnH4 with a plus, and hydroxide is OH with a minus charge. I'll write that as +1 and -1 just to be sure. So I crisscross. Bring the 1 from there down. I'm going to bring 1 from there down to the left. And I'll write NH4 OH next to itself. Again, the 1 from the NH4 goes down, and that would be written over to the side here. We would put it in parentheses if we had to, but it's only 1, so we don't have to. And the 1 from the OH goes in over there. And again, there's 1 of the NH4. We don't need parentheses because there's 1 of each thing. So it really just would be NH4OH. I'm just going to write this again a little bit closer because I left a little bit of space there. So NH4OH, they're all friends, they won't be close. That's what ammonium hydroxide looks like. We got the ammonium part over here, the hydroxide part over here. And any one of these examples on this page, you should be able to go backwards, use the formula, use the rules for naming formulas we've seen the last day or so, and go over them and get that same exact name that we started with. Copper 1-phosphate, almost done. Copper is Cu. It's telling us what the charge is. It says it's a +1, so I'm going to write +1. I can check my periodic table. I'm going to flip to that for 1 sec, and it says copper can be +1 or +2, so this is in fact correct. That's accurate, that it can be a +1. And then phosphate, notice it does not have an IDE ending, so it's not just a non-metal. This is going to be another polyatomic ion. So on table E, I'm going to look for phosphate, and it tells me that phosphate is PO4 with a -3 charge. I can take the charges and drop them down, do some crisscross. So it would be Cu, PO4. The +1 charge from copper goes down next to the PO4. We don't have to write it because it's just 1. And the 3 charge from phosphate goes down next to the copper. So write it right there. And my final molecule is Cu3PO4. I need 3 of the coppers with a +1 charge each, +3 total, to balance out the single PO4 with the -3 charge, -3 overall. So Cu3PO4 is copper 1-phosphate. And the last one, barium sulfite. Barium is element Ba, and it is in the second column, group 2 of my periodic table. So I will look it up, and it's going to tell me that it's a +2 ion. And then sulfite, again, be careful, it doesn't say sulfide. It's not that you change the IDE ending. So this is going to be a polyatomic ion. You can always check your table if you're not sure, but sulfite is on table E, and it tells me it is SO3 -2 charge. So I'm going to take these elements, write them down below. BaSO3. I'm going to take the 2 from here, bring that down, break the -2 from there, bring that down. So put 2 right there, 2 right out there. It would need parentheses to show 2 of the entire thing in parentheses. But again, the 2 and the 2 cancel each other out. So I can erase those parentheses, erase that 2, erase these parentheses, erase that 2, and my entire molecule for barium sulfite is just BaSO3. There's the barium part, there's the sulfite part. You don't need to use any kind of Roman numeral for barium because it only has one option, only has one actual charging form. So BaSO3 is barium sulfite. Hopefully these make a little more sense by now. If you've been watching for 34 minutes, you've seen me do a lot of them, so hopefully you can go feel a little bit more comfortable doing these, and we'll do a bunch more tomorrow.